we're looking at, and we're still looking at it, but we're going to finish it today, and hopefully, well, not hopefully, we will get it finished today. So what's the difference? We are going to look at how to find volumes of revolution when you rotate an area about a line parallel to the x-axis or to the y-axis. So we're not going to take an area and rotate it about the, the x-axis or about the y-axis. What we're going to learn today is how do you rotate the area about a line that's parallel to the x-axis or to the y-axis. And so let's show you one. This one, nope, a mistake. I think they start around about question 7 or 8. Let's see. Yeah, it starts around about question 7 or 8. So anyway, let me tell you the formula before I forget. There are two versions of it depending on whether it's parallel to the x or parallel to the y. So if it's parallel to the x-axis, then your formula for calculating the volume is going to be the integral from a to b pi, the big radius squared, subtract the small radius squared, dx. And we'll get into details what the heck that is. And if you're doing it, but it's parallel to the y-axis, it's going to be the integral from c to d of pi, big radius squared, take away small radius squared, dy. So basically it's the same formula, isn't it? So if you remember that one, I'm sure you can figure this one out. So what did that type of question look like? Well, suppose I did, let's see, I want one that's, yeah, that'll do. This is a question 7, or at least version of question 7. We're going to do y equals x squared. We're going to do x equals y squared. And we're going to do it about, so we're going to rotate about the line y equals 1. No, let's make it harder. Let's make it 2. Yeah, that's better. Right, so the first thing you're going to do, essentially what I'm calling step 1, is draw the thing. I don't think there's a shortcut here. You really do need to draw them because you've got to be able to tell, looking at it, what the curves are. So if you plug that into Desmos, I think you could figure out y equals x squared, right? Can you trust me that x equals y squared looks like that? So the region that we're going to be rotating is this region here. So far, so good. Now, the line that we're going to rotate it about is down here. It's down here, x equals 2. I'm going to rotate it about this fella. So this is a rotation about the y-axis, isn't it? Agreed? Now, the formula for rotating about a y-axis is the integral from c to d pi, a guy called the big radius, it's me, someone just turned up, big radius squared, take away small radius squared. So here it goes. For this shape, if you rotate it parallel to the y-axis, you're going to do the dy formula, and you are going to do from y equals c to d, means from 0 to that point there, which happens to be 1. So you're going to go from 0 to 1. The pi I'm going to stick outside. Now, when you're doing parallel to the y-axis, your rectangle goes this way. And the guy I'm calling big and small is the distance from the axis of rotation to the top of the rectangle and the axis of rotation of the second curve. So one of the curves will be the small distance, the other is going to be the big distance. So in this case, this one is the small one, right? And this one up here is the big one. So we need to know in terms of y, how far it is from there to there. Okay, and how far it is from here to here. Now that does mean I'm going to have to change one of my equations. This equation up here is also the same thing as that guy. You agree that y equals x squared is the same thing as saying x equals square root of y. Well, let's do the distance from here to this curve. This number, let me show you how I'd do it. Would you agree that total distance from there to there is 2? And that the distance from here to here is basically just the x coordinate. And so that's equal to the square root of y. So the distance I want is that dotted distance. What is that distance from here to here then, based on the fact that that's square root of y and that's a 2? What's this guy?
2 minus square root of y.
This is going to be the hardest part of the question, in my opinion, is going to be creating this integral. Once you got this done, it's actually pretty straightforward. So subtract now. Let's look at the small one. Well, if I do a similar kind of thing with the small one, I know this picture's getting really ugly now, but the total distance is 2, and want this distance to the red guy, that's going to be this one, and that's going to be somewhere like here, and that's going to be x equals, what is the red one? Oh, shooting space. The red one is x equals square root of y. Darn it in space. When you look at the distance, this one here, isn't this one the green one? It's x equals y squared. I wish I hadn't done that in the first question. So that goes there. Now this one here, he's the square root of y, and that's 2, and we want the small distance. And it's a very similar guy. Have you noticed that both of them are to take away the formula of each of the curves? Now, if I continued with that mistake, I would have got the wrong answer. It would have been negative 20 pi or something like that. And you know this is wrong because it can't be negative. But the correct answer would have been switch places. So I could have fixed it at the end, but I'm glad I caught it here. So you find the distance in terms of y for the big one, you find the distance in terms of y for the little one, and you're now looking at this fella. So it's the integral from 0 to 1. Foil this out. subtract, FOIL this guy out. Are you comfortable that this times itself gets you that? If I did FOIL, this is what I'd get. We good? Okay. 4, take away all this. 4, take away 4, gone. What do I have? I have a negative 4y squared. I have a plus y to the 4. Subtract that, negative gets you plus 4 square root of y's, and subtract that gets me negative y. So we finally got to this point here, where the volume of that shape would be this guy here. Power rule, power rule, power rule. How will I get the integral of 4 square root of y's?
Change it to a 1/2 power.
And then do the power rule. So, dot, 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 dot. We've got a lot to get through, so I'm just going to have to finish that one at that particular point. Hopefully you can use the power rule. It's going to be one ugly looking answer. Don't be surprised by that. Some 1739 pi or something, whatever. Scan for another fella. It's question 9, or at least like it. Y equals 27x cubed. And the region we're going to, well, the rest of the information is y is 0, x equals 1, and we're going to rotate about the line x equals 2. So, step 1. 27x cubed, pretty easy to do. Which axes is y equals 0? The x or the y?
X.
Yes. So you're going to do y equals 0 is the x-axis, and x equals 1 is that line, and there is the region that we are going to rotate, and we're going to rotate it about another one. So I'll try and get this one right. Agreed, parallel to the y-axis. So we're now into step 2, which is set up the integral. So it's going to be the integral. Don't know why I did that. Right, now if you're going to do this particular guy parallel to the y-axis, aren't you going to have to draw a rectangle that looks like this fella? Agreed? And where do the y values go? Well, they start at 0, but don't I need to know that y value? So what number is that? Well, if you plug in 1, you get 27. So the y values are going to go from 0 to 27. We're going to do big, take away small. So everything has to be written in terms of y. So we're going to have a guy that goes to the top. That's going to be the small fella. And then won't we have a second one going to here? And that's going to be the large, whatever I called it, the big. There we go. So y goes from 0 to 27. Okay, let's do the small one. What's the distance from the axis of rotation to there? Isn't it a fixed number? It's the same every time. Agreed. So that one was easy, just 1 squared. Now it gets a bit messier. See that guy there? I'm going to find this distance here. That's basically the x coordinate, which means I'm going to have to turn this into x equals to be able to figure out what that is equal to in terms of y. So it's y over 27 is x cubed, but isn't x cubed, if you take the cube root of both sides, you get that, and that simplifies out as 1/3 the cube root of y. So let's see, the distance to here is 1/3 cube root of y. The distance to here is 2. The distance I want is this piece. 2 take away that. That's the integral setup. The distance from the axis of rotation to the furthest away curve minus the distance from the axis of rotation to the nearer. In this case, the curve was actually a straight line. Now, take this just a little bit further before I'll do my dot, dot, dot.
Shouldn't there be a pi in there?
There should be. Thank you. Why am I converting this cube root into a fractional power? Why do you think I'm doing that?
It's easier to integrate, right?
Yes, and easier to FOIL as well. So if you FOIL this out, you're going to get 4. Take away 2/3 y to the third, plus 1/9 y to the 2/3, subtract 1. So the only tidying up, and it's quite minor, was the numbers. So just like he said, can you see that if you're going to do the power rule, you don't want cube roots, don't you want 1/3 powers? And so won't that be a power rule, and won't this be a power rule, and won't that be a really, really ugly looking answer, but you'll be able to get it. The fact that that number 27 plays well with these at least means that you'll only have fractions with a pi at the end. You won't have like a cube root of 22 floating about, right? That won't happen to you. So at least that's something. Are we getting a feel for this new kind of more complicated rotation question, where we're not rotating about the x or the y axis, but something parallel? And that means we have to introduce this big takeaway small trick. Is there any questions about that particular one? Okay. See what the next one looks like. Okay. Oh, yeah. I remember this one with the other class. Y equals 2 plus secant x. The x's are going to be from negative pi upon 3 to pi upon 3. There's going to be a y equals 4, and the whole thing is going to be rotated about the axis y equals 2. I think Desmos definitely comes into its own here. So I'm going to go and use Desmos to sketch this thing so that we can get an idea of what the heck it looks like. And is Desmos around? Of course not. Why should it be around? You're going to have to wait a few seconds because I have to actually find Desmos. Okay, I got it now. So here it goes. You can certainly do this on your TI-84. I just think Desmos does a better job. I mean, it's just cleaner. Right, so the function that we're going to do is 2 plus secant x. So y equals 2 plus secant x. That's cool. And y equals 4 is going to be the other piece of the puzzle. And then I'm just going to zoom in. Maybe too much zooming. There we go. The guy that we are interested in is this piece here, right? That's the secant, that's the y equals 4. So you can imagine this area in the middle here that looks like a boat. So I'm drawing, I'm attempting to draw anyway, what that might look like. And you'll see it in a second. Now, we are going to rotate this thing about the line y equals 2. So let me put that one in as well so we can visualize where it is in relation to everything else. All right, can you see the green line? So this region up here is going to be rotated about the line y equals 2. So I'll now come back out and show you my very badly drawn sketch of that picture. But even if it is badly drawn, it still does its job. We are trying to find that region rotated about that line. Great. Now, this guy is parallel to the x-axis. So our volume formula is going to be the value of x from A to B, pi, big guy squared, small guy squared, dx. Are we cool? Now that means everything is in x's. We can deal with that. There's pi. The x goes from here to here. Well, they already told us that, so I just basically put that in. Here's my typical rectangle. The distance from the axis of rotation to the first curve, we're calling the small guy. And the distance from the axis of rotation to the second one, which happens to be a line here, is called the big one. So, big squared, take away small squared, dx. Right, this is a very visual kind of question. If you're a visual learner, which I am, I kind of like these things. That distance from here to here, it doesn't really matter where I put my rectangle. Would you agree the big distance is the same number? And that number happens to be what, 2? Actually, 4 take away 2 is where it comes from, right? Now, what about the small one? Well, if you take that distance there, it's 2. Actually, if you take that distance there, that's a better one. It's 2. If you take the distance here, it's the value of the function. So it's 2 plus secant x. So the guy we're looking for is 4, take away 2 plus secant x. That picture has just got too much going on, so I'm going to draw another version of it where I'm only focusing on one piece of the puzzle. Here is y equals 2. Here is that guy, finishes at 4. We are trying to find the distance from the axis of rotation to the first curve. And what I'm saying is that that entire distance to that straight line is 4. And that distance from here to here is just the value of the function. So won't this be the difference between those two? So that's where that comes from. If I pull, well, I've already done that part. That's 2. So 2 squared is 4. 4 take away that gets you 2, take away secant x all squared. If you square this, you get 4 minus 4 secant x's plus secant squared x. Four take away 4 goes away. Take away a negative is 4 secant x's. Take away that guy is take away
I'm
secant.
not following how you got 2 minus that secant x. Isn't it 4 minus 2, so that would be a positive 2 plus the secant x?
Oh, so how I got from here to here?
Yeah.
That's what you're asking? Okay, I have got 4 take away in brackets 2 plus secant x. And that's 4 take away 2 take away a secant x. And that's 2 take away secant x.
Okay, I see it.
Okay, now it's very small and very quick. Right, so we're here. Now, typically, this would be easy to do because whatever you got is pretty obvious. Well, some of it is pretty obvious. What's the antiderivative of secant squared?
Tangent of x.
Right, so minus tan x would be that bit. On the other hand, what's the antiderivative of secant x? Well, the answer is I don't know. Remember the standard integrals that we went through, where basically you just memorize a whole load of integrals because they're very helpful. Secant squared was one of those, wasn't it? You just remembered that the integral of secant squared was tan, right? That was what we call standard integrals. The secant x is not in that list, but there are many functions that are not in that list. And for instance, you won't find the integral of cosecant x in that list. You won't find the natural log of x in that list. It isn't that they don't have an antiderivative. It's just that they are not that common. So we're not going to like give you a table. If I tried to do every one that you could do you know that little table they had what, about 10 things in it? Without exaggeration, it could have 40 things in it. You see, it's better to have the 10 most common ones, and that way you'll remember them. So what do? You just go looking for the antiderivative of secant x, and you will find it online, or you will find it in the back of your ebook, and it will just tell you. Off the top of my head, but don't quote me on this because I could be wrong, off the top of my head, I think the antiderivative of secant x is the natural log of secant x plus tan x. But whatever it really is, just figure out what it is and you're done. So what I'm saying here is that if you ever come across an answer that you need to find the antiderivative of something, and it's not an obvious one that you've been told, it's very good chance that it's just a standard integral that you have to go looking up. Off the top of my head, do you want to know what the antiderivative of log x is? It's x log x minus x. You want to know what the antiderivative of cosecant squared is? It's negative cotangent. You want to know the antiderivative? Oh, well, they just go on and on, right? Cos x is sine, hyperbolic sine. And I rambled too much because all I wanted to say is look it up and you get the answer, right? So let's move on. And we'll look at, oh, we haven't done this one. This is a cool one. This is like question 11. It's y equals 2 times the sine of x, and the other curve is 2 cosine x. Thankfully, we're told the x's to use it with, and it's going to be rotated about the line y equals negative x. So that's the guy. So I'm going to just pause for a second, and we're going to look at Desmos again, because there's a lot happening this time. So let's get rid of those ones, and we'll type in y equals 2 times the sine of x. There you go. Two times the cosine of x. And it's going to be about the line y equals negative 1, so I'm going to put that in. Now, we are only interested in the integral from 0 to pi upon 4. So I'm going to move this shape up and down a little bit. Can you see that, well, can you trust me that that point there is actually where x is pi upon 4 lives? So we're doing this black curve, we're doing this blue guy, right? We're doing 0 and we're doing pi upon 4. In other words, it's this funny little, looks like an axe head to me. So just slowly taking a basic sketch of this thing. So it looks something like this, comes up something like that. This is 1, this is 0, this is pi upon 4. And we're rotating about the line y equals negative 1, which is below the x-axis, so it's down here. There we go. So the cosine, oh, I should put the labels on it. This fella here is 2 cosine x. And this guy here is 2 sine x. This is the shaded region from 0 to pi upon 4. And we're rotating about y equals negative 1, which means that it's parallel to the x-axis. So that means my volume is going to be the integral from 0 and x is pi upon 4. It's going to be the big distance, take away the small distance, and everything is going to be in x's. And there's a pi there.
Shouldn't that be a 2 at the top of your graph?
Should it be a 2, did you say? I thought I had done 2. What 2 have I missed?
There's a 1. Just to the left. When it starts.
Oh, you mean
When
up
the
here?
cosine starts.
I gotcha. Yes. Right. If I'd paid more attention to Desmos, I would have written the number down. But you're perfectly correct. Okay, now this picture is going to get ugly really quickly. Whenever you rotate about an axis that's parallel to the x, you draw one of these random rectangles. They're basically the top and the bottom curve, right? won't this distance from here to here, from the axis rotation to the first curve, isn't that the one that we call the small? So far, so good. Now let's see how I'm going to construct this one. The total distance is really made up of two pieces. Would you agree that the distance from here to the x-axis is just 1? You happy about that as 1? Now, the distance from here to here, isn't that basically just the y-coordinate, the y-coordinate? But the y-coordinate of this curve using the x equation for it. So that tells me that I'm going to use this guy and I'm going to use this guy. Do I add those two together to get this distance or subtract them in this question? Is it going to be
You
1?
add them.
Yes, you do. Would you agree? Sometimes you subtract, sometimes you add. Doesn't depend where it is. You know, if the line was up here where that pen is, do you know you'd end up subtracting some stuff? If it's down here, you end up adding stuff. So it's going to be 1 plus 2 sine x. Okay, now the big guy. I won't draw it in because if I did, the picture would just be extremely ugly. But can you imagine going from there to the top curve, right? From there to the top one. Won't I do a very similar thing? Won't I break it into 2 bits? The first piece takes you to the x-axis, and that's 1 unit. And then won't the second piece just be the y-coordinate written in terms of x? And that is 2 cosines. So you're going to have a 1 plus 2 cosine x. Do you notice that they're very similar? They're always similar. The way you get one is pretty much the way you get the other. Are you comfortable about the creation of that particular question? Big and small. Right. Couple more lines and I'm going to have to leave it. Foil this guy out. You get 1 plus 4 cosine x's plus 4 cos squared x's. Take away 1 plus 4 sine x's plus 4 sine squared x's. One take away 1 gone. 4 cosine x's take away 4 sine x's. Plus 4 cos squared x's take away 4 sine squared x's. Okay, let's talk about integration here. Antiderivatives. You can find the antiderivative of 4 cosine. It's 4 sines. You can find the antiderivative of negative 4 sines. It's 4 cosines. You cannot find directly the antiderivative of that guy or that guy. So what are we going to have to do to fix that problem?
Split it up and use a U sub.
Well, that's always a strategy for many equations, but in this one that won't work. Any other suggestions? How am I going to find the antiderivative of this guy? That's the puzzle. U subs won't do it. There's not a U sub that would save it. Trig identity is how we're going to do it. Does anybody remember a way back in the day where you did trig that there was a double angle formula and that cos squared x take away sine squared x was equal to something?
Isn't it 1?
If it was plus, you'd nail it. It would have been 1, but it's negative and that makes it different.
Cosine
have-
2x.
I hear
Cosine 2x?
cosine. I hear cosine 2x. So won't 4 of them get you 4 cosine of 2x's? So this guy needs one more line. if cos squared take away sine squared, if that's cosine of 2x, can you see why 4 of them would get you 4 cosines, 2x's? Right, now we're ready. Antiderivative, check. Antiderivative, check. Uh-oh. A little hiccup, but not a major one. How do you find the antiderivative of 4 cosine 2x? And someone's actually mentioned it earlier. The
Use
method.
a U sub.
Now you use a U sub. And the U sub will just be 2x, right? Do you see how much work there is in this one question? Creating the picture. Figuring out who the big guy is in terms of x, who the small guy is in terms of x. Doing a bit of foiling out. Collecting terms. Using some trig identity. And then finally after this, you still have to integrate and then plug in pi upon 4s, which means you're going to have to deal with what's the cosine of pi, the exact value for the cosine of pi upon 4 and things like that. So these questions are not going to be quick. So since you've got Monday off, I suggest really strongly that you get up to this chapter done by that time, so that next week you won't be over extended because you'll have got this one out the road, and it is a slow one. We got time. Yep, actually perfect. There's one last question, but question 12 is not a difficult question in the sense what you do is difficult. You just have to figure out what the heck you want them to do. So just try and figure out what is the function that you're trying to rotate about the x-axis. And there's lots of things going on there that are not necessarily helpful. And so you have to know what to ignore to make your life easier.